For the TRC 1204 project, 9 full-scale load tests were performed within the state of Arkansas. 3 of the full-scale load tests were performed on 6-foot diameter drilled shaft foundations, and 6 of the full-scale load tests were performed on 4-foot diameter drilled shaft foundations. These full-scale load tests were completed using bidirectional load cells. The use of an OCell prevented the need for a large load frame with static weights or for reaction piles. Using an OCell, the loading mechanism was located beneath the ground instead of above the ground. For this project, 13-inch or 16-inch OCells were used for the 4-foot diameter shafts, and 20-inch diameter OCells were used for the 6-foot diameter drilled shafts. The OCells were capable of providing nominal loads in the upward and downward directions of 875 kips, 1,425 kips, and 2,250 kips, respectively. When assembled, a typical OCell consists of the blue hydraulic jack, with the hydraulic hoses that go from the jack to the surface, and 2 plates, a top plate and a bottom plate. The hydraulic jack is usually assembled to the steel plates in the field, while the rebar cage is being fabricated. Number 11 bars were utilized for the reinforcing steel within the rebar cages for this project. At the Siloam Spring site, permanent templates, wheels, were used to hold the longitudinal reinforcing steel prior to the transverse hoops being tied around the longitudinal steel. As shown here, a temporary lifting hook was attached to the OCell to move the OCell into position on the bottom plate, and then the lifting hook was removed prior to placing the top plate onto the load cell. A typical finalized load cell looks like this. Note, the holes within the plates of the OCell were used for the Tremie tube to travel through the OCell to place concrete below the OCell. Although thermal integrity testing for drilled shafts is becoming a more common method for identifying the constructed size of the drilled shaft and the location of any anomaly within the shaft, cross-hole sonic logging tubes, hereinafter referred to as CSL, was utilized for the shafts that were constructed in association with the TRC 1204 project. Following completion of the rebar cage, but prior to placing the rebar cage into the excavated hole, 4 CSL pipes were added to the rebar cage of each drilled shaft. Telltale pipes were also added to the rebar cage prior to the cage being placed into the excavation. As discussed later, these telltale pipes were utilized to determine the amount of movement of the top plate and bottom plate of the OCell. Dumbbell strain gauges were also added at various locations and attached to the rebar cage before the rebar cage was picked up and placed into the excavation. These strain gauges were utilized to determine the amount of load shed between the gauges during the full-scale load test. All the rebar cages were picked up using at least 2 pieces of equipment, typically a crane and the drill rig. Depending on the location of the OCell was either placed into the rebar cage while the cage was on the ground, as is the case at Turl and Monticello, or placed into the cage after the cage was picked up but prior to the rebar cage being placed in the excavation, as is the case at the Siloam Spring site. For all of the shafts at each of the sites, the top of the bottom plate of the OCell was greased to ensure a clean break of the concrete at this location when the hydraulic jack was inflated. The tops of the telltale rods and the tops of the CSL tubes were covered with duct tape to prevent concrete from infiltrating into these tubes. The pump truck was then connected to the Tremie pipe, and concrete was placed from the bottom of the hole to the top of the hole. A constant head of concrete was maintained above the tip of the Tremie tube while the Tremie tube was being pulled from the excavation as the excavation was filled with concrete. Joints were removed from the Tremie tube as the Tremie was removed. Likewise, the Tremie was disconnected and reconnected to the pump truck as the temporary casing was removed from the excavation. Concrete was also poured over the top of the temporary casing to ensure that no segregated concrete was located within the concrete when the casing was removed. Following construction, the drilled shafts were tested. The CSL testing was performed by simultaneously removing an emitter and receiver probe from the water-filled CSL tubes. All possible emitter and receiver combinations were utilized to obtain waterfall plots. This is the travel time as a function of depth as the probes were removed from the CSL tubes. LVDTs and automatic levels were also utilized to monitor the upward and downward movement of the drilled shaft during the full-scale load tests. A hydraulic pump connected to an air compressor with a flow rate of 185 CFM at 125 psi was utilized to inflate the hydraulic jack to 10,000 psi. The LVDT gauges, strain gauges, pump pressure, and automatic levels were recorded using a data acquisition system. From the full-scale load testing, several plots are typically developed. These plots include the OCell results, the top-down load shed curve as obtained from the strain gauges, the upward and downward nominal capacity as a function of movement, and the top-down axial capacity curve. It is important to note that the top-down axial capacity curve was developed by adding the amounts of axial capacity in the upward and downward direction at the same amount of movement.